If you spent time around macroeconomics, you've probably seen this, 1 over 1 minus MPC. You probably know this as the spending multiplier. But what I want to talk about today is, why is this the spending multiplier? So when it comes to talking about the spending multiplier and how we arrive at 1 over 1 minus MPC, there's actually two different ways that you can derive that. The first of all is looking at it through the lens of an infinite geometric series. And the other way we can get to this is through deriving it through the GDP formula. And I want to spend time looking at both of them, but we're going to start off looking at it as an infinite geometric series. When it comes to an infinite geometric series, you might see something that looks like this, because this is kind of that exact equation proof for an infinite geometric series. But there's a lot of stuff going on here. And so I want to break down what each of these pieces mean, because it'll better help us understand the spending multiplier. So let's start over here on the left. We have this letter A. Now, A is our first term in our series. And when we say the first term in our series, when it comes to economics, what we mean here is it is the dollar value of the change in spending that occurs. So maybe when it comes to government spending, there's some initial change in government spending that occurs, and we're using the spending multiplier in order to try to understand, well, how much of an impact does that change in spending have on our total GDP? As you know, with the spending multiplier, we need that MPC. The MPC here is actually going to go in there where our R is, because R is some common ratio or percentage. Because that spending, as we know, when it is spent, every time it is, in a sense, respent, it's not all of it being respent, but some percentage. And that percentage that we're talking about here is the marginal propensity to consume, our MPC. And so R here in this formula, it is some common percentage for us in economics. It's going to be our marginal propensity to consume, or our MPC. Now, another thing I want to point out, though, is this qualifier that sits here on the end, where it says if the absolute value of R is less than 1. And so what this is saying, the sum of A times R to the nth power is equal to A over 1 minus R, but that's only true if the absolute value of R is less than 1. Now, for us, since the R is MPC, what we're saying is the absolute value of that needs to be less than 1, which for us it is. So we're going to be fine there, because typically, again, you see MPC written as, 0.8 or 0.6. And so this is going to be true for us, and so we're good to continue working through this. Now, over here to the left, what we end up seeing is this sigma here. And this sigma, what it means is we're taking the sum, if we take A times R to the nth over and over and over, where every single time that we're adding a new A times R to the nth, n is increasing by 1, starting at 0. So we start off with A times R to the 0th power plus A times R to the first power plus A times R to the second power, and we just keep going and going. And the infinity symbol at the top stands for, we're going to keep doing this all the way up until n equals infinity. And so it's just going to keep on going and going and going. Now, as we go throughout this, we're going to rewrite this whole thing right there as the letter S, which means it's the sum of the series. But again, when we talk about this in economics, this should make sense to us, because what we're trying to do is we're trying to add up that spending that occurs over and over time, like that multiplied effect of the spending as money is spent, and then it's respent from there and respent from there. But again, it's always in smaller and smaller and smaller percentages because of that MPC, which is less than 1, right? And so that's what we see in this sum. We're just adding those up over and over. But like we understand with the multiplier, that can be simplified into that A over 1 minus R. And so whenever we get to this end part here, what that is saying is that the final result of all this is going to equal the total multiplied effect that's going to be had on the economy as a whole, right? That's what the final sum of this series is going to give us. Now, if you notice on the right side there, it says it's equal to A over 1 minus R, and that doesn't exactly look like our spending multiplier, because that actually includes our initial spending up there in the numerator. And so we're actually going to separate the multiplier from that initial spending a little bit later on. But now that we understand what some of these different pieces of this are, let's go ahead and start to kind of break it down. So we said that what we're trying to do is we're trying to sum A times R to the nth power over and over and over. We're adding all those up, where you increase n by 1 every single time. So the sum of our series is equal to, first of all, A times R to the 0th power. And so A times R to the 0, well, anything to the 0 power is just 1. And so that first term is actually going to be A for us. And then we add next our a times r to the first power. So a times r to the first power, again, something to the first power is just itself, so we have a times r. From there, we add in a times r squared. And that's just going to be a times r squared. And we keep on going, and we can do that with a times r cubed. And we can just keep on going down the line, but how long until we eventually stop? Well, as you know, we go all the way up until we get a times r raised up to infinity. And for us, because we know we're taking that with n, and n is, it's going all the way out to infinity, we're just going to write that last term as a times r to the nth power. And so there you have it. You have the sum of this entire series. And so if you were to add up all of those pieces, a plus a times r plus a times r squared, all the way up through, that is going to give you the total impact that our initial spending has on our GDP. But again, that's a lot of addition. We need a way to kind of simplify this down. So what we can do from here in order to simplify it is we can sort of get rid of some of those terms, and we're going to do that by subtracting out the sum of the series. Now, if we were to subtract it out by the sum of the series itself, it's just going to leave us with absolutely nothing. And so what we're going to do instead is we're going to subtract it by the sum of the series times r. Remember, r is our MPC here. We're going to multiply it by r. And so we're going to multiply each one of those terms on the right by r as well. So that first term, instead of a, it becomes a times r plus a times r squared plus a times r to the third, and so on. Now that last term there, I have it written as a times r to the nth. Now, remember, technically what that term was before, it's actually a times r to the n minus 1 times r. That's where that extra r comes in. And so that's why we actually have to add on one more term here at the end, and that term is a times r to the n plus 1. So like really it's like infinity plus 1. We're going one more. Now the reason we do this is because as we subtract the sum of the series minus r times the sum of the series, what that actually does is it starts to cancel out some of those terms to simplify this for us. Because as you can see, a times r, that's going to cancel, and then a times r squared is going to cancel, a times r cubed is going to cancel, a times r to the fourth, and so on and so forth, all the way up until we get the a times r to the nth powers canceling out. But that's the last thing that cancels out here. And so what we can then do is rewrite what's left. On the left side, we have s minus r times s, right? And then on the right side, we have a up top minus a times r to the n plus 1 power. So far, we've got this set up, and we've simplified out a lot of those, there was a lot of terms there, but what we've started to do is be able to simplify this a little bit. So now that we've done that, we can even simplify a little bit more. So for example, if we look at the left side of our equation there, we can see the sum of the series, s, there in a couple places. So we can factor that out, and we get s times 1 minus r on the left side. And then we have an a that we can factor out on the right side, and we get a times 1 minus r to the n plus 1 power. Now, once we do that, we're ready to move on. But before we move on, we've got to remember that if statement up here. So that if statement saying the absolute value of r is less than 1. Now the reason this is important is because if you notice in that r term, n is tending toward infinity, right? And what happens as that power gets bigger and bigger and bigger? Well, for numbers like you're raising to the second, third, fourth, and all the way up to the infinity power, for numbers greater than 1, that would tend toward infinity. But since it's less than 1, it actually converges to 0. And that should make sense to us, because if you take 0.5 times 0.5, you get 0.25. And then you multiply it by 0.5 again, you get 0.125. And then multiply it by 0.5 again, you get 0.0625. And as you keep multiplying it by more and more and more and more and more, or as you're raising it to higher powers, what it's going to do is it's going to converge to 0. And therefore, we can rewrite this even further. We can write the left side again as s times 1 minus r. And then the right side we can rewrite as a times 1 minus 0, because r raised to the n plus 1 power is going to be 0. So once again, we can clean this up a little bit. That left side is going to stay the same, but that right side, we can distribute that a. And so we have a times 1 minus a times 0. And then we got one more thing we can do. We can divide both sides by 1 minus r, because that way we're solving for the sum of the series, right? That's ultimately our goal. And so we're leaving s over there on its own, because the 1 minus r's will cancel. And then on the right side, a times 0, that's just going to be 0, so we don't need that anymore. And then when you rewrite what's left, we have the sum of the series is equal to a divided by 1 minus r, which is the proof that we needed. Like that's what it ultimately says up above, right? That the sum of a times r to the nth power equals a divided by 1 minus r. But there's still one more thing that we need to do. So once we get this here, what we can then do is pull that a out in front. Because remember, we said a is the initial spending there. And so as we pull a out in front, this is where things are going to really start looking familiar. Because we have a times 1 over 1 minus r. But keep in mind, r is our common percentage. And what is our common percentage? It's MPC. So we can go ahead and substitute MPC in there for r. So now that we have this, again, should really start looking familiar, because off to the right side here, we have our spending multiplier. And we say our spending multiplier there times a, whatever that initial spending is equal to the total multiplied change that happens in spending to our GDP. And that's exactly how we use this spending multiplier. So let's go ahead and take a look at this now that we understand it using a real life example. Suppose that the government had increased spending by $150 billion and the economy's MPC is 0.8. Calculate the total change to GDP. All right, so on the left side, we're going to kind of, instead of writing S for some of the series, we know that what that represents for us. So we'll write it as our change to our real GDP. And then we're going to start adding up those different parts of that series, right? So a times r to the 0th power. Now for us, we actually can substitute numbers in. We know a, the initial change to spending, is 150 times our MPC of 0.8 raised to the 0 power, plus a times r to the 1st power, which again is 150 times 0.8 to the 1st power. And then we can go on and do that to the 2nd power, and then we can do that all the way up until we get to the nth power. Now once again, we can rewrite this. We know that 150 times 0.8 to the 0th power, well, anything raised to the 0 power is just 1, so that's going to be 150, plus 150 times 0.8, which is 0.8, and then squared, we can leave that one there, all the way out to the nth power. And so now that we have this all written, we have the sum of that series. But again, we don't want to add this up. We want to be able to simplify it a bit more. So just like we did before, we subtracted out the sum of the series, but it wasn't just the sum of the series, so it's not just going to be change to real GDP. It's going to be change to real GDP times r, or in this case, our MPC of 0.8. So when you do that, now, instead of 150 as that first term, you have 150 times 0.8, and then 150 times 0.8 squared, and so on and so forth, all the way out so you get 150 times 0.8 to the nth power, and 150 times 0.8 to the n plus 1 power. But once again, things will start to cancel out. So those will cancel out, squaring the terms cancel out, raising it to the nth cancels out. And what that leaves us with is on the left side, change in GDP minus 0.8 times the change to GDP is equal to 150 minus 150 times 0.8 raised to the n plus 1 power. And again, we can factor out some things here. So we'll factor out the change in GDP, and then multiply that by 1 minus 0.8. On the right side, we'll take 150, factor that out. So we have 150 times 1 minus 0.8 raised to the n plus 1 power. But remember, since 0.8 is less than 1, we know that 0.8, as you raise it to higher and higher and higher powers, is going to converge to 0. And so we can just rewrite the right side of that equation as 150 times 1 minus 0, or change to real GDP, times 1 minus 0.8 is just equal to 150. And now that we have this, we can pretty well calculate what is going to be the change to our real GDP. We're going to start off by dividing both sides by 1 minus 0.8, and so that's what you get on the right side. And then again, pull that 150 out in front, and so we have the change in the real GDP equals 150 times 1 over 1 minus 0.8. So since we have our spending multiplier right here, and we know our initial spending is right here, we can use those two together in order to calculate what is our change in real GDP. And our change in real GDP is going to be equal to that 150 times 1 over 1 minus 0.8, which 1 over 0.2 is 5. And therefore, we can calculate that as a result of $150 billion change to our government spending, times that multiplier, it's going to give us a change in GDP of $750 billion. As I said, though, that wasn't the only way that we can actually derive that multiplier, we can also do it by using our GDP formula. And so this one requires a little bit of calculus and actually finding the derivative of an equation. And so that's what I want to look at in this final part. So you know our GDP formula. We have y equals c plus I plus g plus x minus m. But what I want to do really quickly is I want to look at the c right here, and we're actually going to rewrite the c a little bit different for these purposes. And what we're going to do is we're going to rewrite it in this way. So y equals c plus r times y minus t plus I plus g plus x minus m. Now there's a bunch of new letters in there, and I kind of want to explain what we got going on. So c right there, the lowercase c, I'm using lowercase c for autonomous spending or autonomous consumption. A lot of times people use a lowercase a, but we already used that for something else in this video. So that's why I'm using a lowercase c. Now autonomous consumption is just that consumption that you do no matter what, even if your disposable income is at zero, right? So like you're paying your rent for food, those types of things. If you remember from that aggregate expenditures model that you maybe have seen, autonomous consumption is wherever our y-intercept is there, wherever our level of consumption that we do even when disposable income is zero. And then R, once again, still stands for MPC. And that term in parentheses there of y minus t, that actually stands for our disposable income because it's our income beyond that minus those lump sum taxes. And we're using lump sum just to say like any of those taxes you have to pay because your income that's left over after taxes is that disposable income that you have beyond that. So now that we've got those figured out, we're going to use this then in order to derive our multiplier. What we want to do first is take that r, and we are going to distribute that r, the lowercase r in there. So we have c equals r times y minus r times t plus I plus g plus x minus m. Now, what we want to do is we want to solve for y. And so we need to start by subtracting r times y from both sides, and you get on the left side y minus r times y equals c minus rt plus I plus g plus x minus m. From there, what we can do is we can factor out a y on the left side, and so we end up with y times 1 minus r equals c minus rt plus I plus g plus x minus m, and then divide both sides by 1 minus r. Now what I'm going to do, instead of putting that whole right side over 1 minus r, I'm just going to write in y equals 1 over 1 minus r times the rest of that stuff. Now once we have that, what we have is we have our GDP formula. But remember, we're not trying to determine what is our GDP. We're trying to find the change in our GDP. And if you maybe remember from calculus, the way we can find change in things is by taking the derivative. And now what we want to do here, though, is since we're trying to find the derivative or the change in our GDP, and we're doing that with respect to G, though, because if you remember, G is our change in government spending. So for every bit of change to government spending there is, what change does that have on our GDP? And so we can rewrite this as d of y over d of g, so change in y over change in g. And then again, we're taking the derivative of that right side of the equation. And so when you do that with respect to g, that first term with c leaves us with a 0 there. Doing it with rt also leaves us with a 0. Doing it with I also leaves it with a 0. But when we take the derivative of y with respect to g, and once we hit the g on the right side, that leaves us with a 1, right? And that'll be important later. And then we got a 0 again from our net exports, x minus m. And so all those zeros kind of disappear from there, and that just leaves us with this. The last two things we need, the d of y over d of g equals 1 over 1 minus r times 1. So since this is the last thing we have, we can kind of start to rewrite this, because remember, right there, that r, if you remember, is our MPC. And so therefore we can sub in MPC for r, and we get the change in y over change in g is equal to 1 over 1 minus MPC. And that's exactly what the multiplier is, right? Like this right here, which is our spending multiplier. What our spending multiplier is it tells us, hey, for every bit of change that happens to our government spending, right, what is the change in our real GDP? What's the change in our real GDP that occurs for every change in government spending? And the ratio of those is the spending multiplier, right? Because that's what it tells us. Like for every dollar change in government spending, the change in GDP is going to be whatever the spending multiplier is times bigger. So let's go back to our example we had. Government spending increases by 150 billion, MPC of 0.8, calculate the total change to real GDP. So again, we have change in y, d of y over d of g equals 1 over 1 minus MPC. But let's sub in what we know. We know that the change of government spending, so d of g, is 150, and that equals 1 over 1 minus 0.8. We also know that 1 over 1 minus 0.8 is going to equal 5. And then it just becomes a simple fraction, where we're missing one number, where we can plug in and solve, right? And so we know here in this case then that d of y is going to equal 150 times 5. We then know that d of y is equal to 750. And remember, d of y, in this case, y is our GDP. So d of y is actually our change in real GDP, and that's equal to 750, which is exactly what we had determined before. And so those are, again, just kind of the two main ways that we can derive that multiplier. But sometimes I think it's helpful to be able to go through and see, hey, actually, where does this multiplier come from?